Imagine a machine flying 1,500 kilometers away from its launch point. It stays just a few meters above the Earth, hugging the mountainous terrain, completely unseen by radar. Over the last 40 years, long-range cruise missiles have become the primary method for projecting power across the globe, allowing nations to strike deep into enemy territory without risking a single human pilot. This map shows a 1,500-kilometer radius circle expanding from a single launch point, illustrating the massive geographical reach these weapons offer to a military commander. Today, 3 specific weapons dominate this space: the American Tomahawk, the Russian Kalibr, and the Chinese CJ-10. Mainstream news coverage often treats these names as interchangeable tools of destruction. Stripping away the geopolitical theater to look strictly at the engineering reveals that each superpower accepts distinct technical trade-offs to build a missile optimized for their specific military doctrine. To understand how a nation plans to fight its next war, you have to look past the explosive payload and examine the complex, autonomous navigation brain that guides the weapon to its target. The second a cruise missile leaves its launch tube, it relies entirely on an inertial navigation system, or INS. An INS is an internal tracking unit that calculates the weapon's position based purely on its own motion, using gyroscopes and accelerometers. Because the INS does not need to receive any outside signals to work, the missile can navigate through heavy electronic warfare. The enemy cannot jam a signal that does not exist. However, relying purely on internal sensors creates a challenge. Tiny measurement errors build up over time, meaning that over a 1,500-kilometer flight, an uncorrected INS will cause the missile to miss its target. To fix this drift, engineers integrated a second system called terrain contour matching, or TERCOM. TERCOM is a navigation method where the missile uses an altimeter to scan the topography below and compares that physical profile against preloaded digital maps. This split-screen visualization shows exactly how that works. On one side, a topographical line scans the physical terrain, while the other side continuously matches it against a stored digital grid to correct the flight path. Because the missile constantly knows exactly how high the ground is below it, it can safely drop down into valleys and fly below the horizon line. By dipping tightly into these terrain features, the weapon stays physically underneath the expanding waves of high-altitude enemy radar. Engineering a missile to fly this way keeps it survivable in contested airspace. The trade-off is that the launching nation must spend billions of dollars maintaining and continuously updating a massive database of digital maps for every potential conflict zone on Earth. To maintain a precise track over hours of flight time, modern cruise missiles also pull down position updates from satellite networks in space, like the American GPS, the Russian GLONASS, or the Chinese Beidou. A few successful satellite pings during the mid-flight phase will refine the missile's accuracy down to a margin of just a few meters. But as the weapon approaches the final target area, the airspace is usually saturated with defensive electronic warfare. Adversaries actively broadcast noise to block those satellite signals in the crucial final seconds of the strike. To guarantee impact even when completely jammed, advanced missiles rely on a terminal system called DSMAC. DSMAC is a final phase targeting system where the missile uses an optical camera to visually match the physical target against a stored reference photograph. This point-of-view camera feed illustrates the process, as the onboard computer analyzes the structural target and locks a tracking box over the exact impact zone. While optical recognition provides sub-meter precision, it relies on clear visibility. As thick clouds or heavy smoke roll over the target area, you can see the tracking box struggle to maintain its lock on the structure. No single guidance method is perfect. The INS drifts, radar can be avoided, satellites get jammed, and cameras can be blinded. This 4-step navigation stack is mandatory because if one system is blinded or jammed, the others must compensate to ensure the strike. Every modern military uses that baseline navigation stack, but the United States, Russia, and China physically tweak the hardware to prioritize different outcomes on the battlefield. The American Tomahawk is the established standard-bearer for precision surgical strikes. The Tomahawk's distinct advantage comes from its extensive operational history. From the 1991 Gulf War to the Syrian Civil War, The United States has fired thousands of these weapons, providing Raytheon engineers with decades of real-world combat data to continuously refine the navigation software. But the Tomahawk trades speed for that high precision and reliability. Its strictly subsonic flight profile means it travels at roughly 880 kilometers per hour, giving modern layered air defense systems a wider window of time to track and intercept it. Russia took a different engineering path with the Kalibr family, designing a weapon focused on multi-platform flexibility and maximum standoff distance. To achieve a massive operational range of up to 2,500 kilometers, Russian engineers accepted a slight reduction in absolute pinpoint accuracy. They also engineered specific variants of the Kalibr to accelerate to supersonic speeds in the terminal phase, using sheer velocity to punch through enemy defenses right before impact. China's CJ-10, developed by the China Aerospace Science and Industry Corporation, prioritizes a completely different launch environment, land-based deployment. By mounting these weapons on heavy, multi-wheeled trucks, the Chinese military creates a highly survivable, mobile arsenal. These launchers can hide deep inland, drive to a firing position, and relocate before the enemy can trace the origin of the launch. The primary unknown factor for the CJ-10 is its lack of public, real-world combat verification. Unlike the Tomahawk or the Kalibr, there is limited unclassified data on how its guidance stack performs under active, chaotic wartime conditions. The variations in speed, range, and launch platforms show how each superpower has tailored its engineering to support its specific national defense priorities. There is no single best missile, only the optimal fit for a doctrine. This chart measures reliability against flexibility. Tomahawk's high reliability anchors a naval precision doctrine. Kalibr's multi-platform range optimizes a standoff doctrine. The truck-mounted CJ-10 provides inland stealth for an asymmetric doctrine. The invisible fusion of AI, space technology, and physics allows these weapons to bypass modern defenses and strike across thousands of kilometers.